Welcome our viewers. Welcome to Molten Aid Educational Services. My name is Teacher Chanogora Moses Udilegage. I will be taking you through physics. This topic called simple harmonic motion. Of course, we shall start by knowing what simple harmonic motion is. When we talk of simple harmonic motion, it is a periodic motion where the acceleration is directly proportional to the displacement from a certain fixed point. In other words, we shall call it an equilibrium point. Mathematically, we represent simple harmonic motion as A is equal to A is directly proportional to negative x, where our x is the displacement from a certain fixed point and our A is the acceleration of the motion. Now, introducing the constant of proportionality, we shall have acceleration A is equal to negative mu squared x. Now, the significance of this negative is showing that both acceleration and the displacement are in opposite direction. When acceleration is in the other direction, displacement will be in this direction. Now from here, this mu is what we called angular velocity or a simple harmonic motion, and we can define it as the rate of a change of angular displacement with the time. Now from here, let us look into what we called velocity or a simple harmonic motion. When we are talking of velocity of a simple harmonic motion, just like any other velocity, it is the rate of a change of displacement with the time of a body in motion. In this case, we shall consider the body describing simple harmonic motion. From our acceleration here, we shall get our acceleration. From our acceleration here, we shall get our velocity. Of course, we all know that velocity is the rate of change of time, of distance with the time, of displacement with the time, where, first of all, our acceleration is the same as dv over dt. Rate of change of velocity with the time is what we call acceleration, which is the same as negative mu squared x. I already told you what mu is the angular velocity. Through chain rule of differentiation, we can break out this dv over dt to bring some element of a distance, actually displacement. So we shall say dv over dt, but dv over dt is the same as dv over dx dot dx over dt. This is what we call the chain rule of differentiation, and this right hand side is the same as left hand side. If you try crossing out, dx will virtually cross out and we go back to dv over dt. But now we shall not cross it out because the significance of dx over dt is what we call the velocity in the real life. So we shall say this one is the same as v dv over dx. This is our acceleration. Of course, it was derived from here. It is this expression that we shall equate it to negative mu squared x, just that we go on and get our velocity. So v dv over dx is equal to negative mu squared x. So this is our equation, and we shall take this dx there, just that afterward we do integration. In the other word, we shall leave now v to be on its own. So v dv is equal to negative mu squared x dx. This is by cross multiplication, and from here is when we shall now introduce integration. Uh, by integrating both sides, we shall have v dv is the same as negative mu square integral of x dx. We are putting negative mu squared outside because it is a constant, does not depend on x. So this one, if we integrate this one, get it very well. If we are integrating, we increase the power by 1, we divide by the new power. So integrating v dv, we shall have v squared divided by 2. We have increased the power by 1 and divided by the new power is equal to negative mu squared. Increase the power of this one by 1, we get x squared divided by 2. Of course, we don't have limits here, so we put our constant of integration. Let's say it is c. So this c is what we call the constant of integration, and we can determine it through our initial conditions. We know that when the simple harmonic motion is just starting, initial conditions, when t is equal to 0, actually at the start when t is equal to 0, x is going to be the maximum displacement. Sometimes we usually put it to be r. When it is in circular motion, we call this r to be the radius of the displacement, and of course v is going to be 0. So we substitute this one in our equation. Let's say equation 1. We substitute in equation 1 for us to get the value of c. So substituting there, we have v is equal to 0. Substituting there, we shall have 0 is equal to negative mu squared. Now we shall have r squared over 2 because x is equal to r plus c. And in this case, we shall make our c the subject, and c is going to be mu squared r squared over 2. This value of c we have gotten, we shall substitute it back into equation 1. So substituting this value of c back into equation 1, we shall have v squared over 2 is equal to negative mu squared r squared. No, actually not r, it is x squared over 2 plus c, which is mu squared r squared over 2. So this is our general equation for velocity of a simple harmonic motion. We have LCM being 2, 2, 2. We can cross it out and we shall have, mark this one very well, we shall have v squared is equal to negative mu squared x squared plus mu squared r squared. We can rearrange this one. Bring this, we start with the positive one, just that v squared is equal to mu squared r squared minus mu squared x squared. This is just interchange. We take the other one, that side. And from here, we see that mu squared is a constant, and it is a factor of this one and this one. So we can pull it outside, and we shall have is equal to mu squared into bracket r squared minus x squared. This is v squared. Now from here, if we want to make v the subject of the formula, actually this v is our velocity of the simple harmonic motion. What we shall do, we square root both sides. Introducing square root both sides, we shall have v is equal to plus or minus the whole of this one. plus or minus square root of mu squared r squared minus x squared. And from here we can simplify this one, and we introduce now the